Today was set aside for exam number 4 on chapters 6. No, chapter 8. No, chapter 6 and 7, exam 4. So since there's nobody here in class, I assume that everybody else is going to take the exam in Brightspace. So we're going to pick up with chapter 5, exam 5, chapter 9, chemical quantities. And we're going to be using this set of PowerPoints, right? You'll see more of them in just a minute. And in Brightspace, you have access to this review document. Looks like this, right? And then there's also a key to this review document in Brightspace, which I didn't print. And if you, as usual, if you can't figure out why you're getting certain of the problems wrong, then go to this worked problems document. And it'll show you at least one way that I solved those problems. And if you still can't get it, either come to class on review day or shoot me an email, or we could schedule a Zoom meeting and iron out these problems. All right, so I'm going to share the PowerPoint set. Go. And one more thing. All right, now let's make a slideshow. There we go. All right. Remember back in chapter 8. Well, let me recap. We've learned the alphabet. In other words, chemical symbols. We've learned how to make words out of those symbols, which in chemistry is the compound. How to name the compounds, how to write the compounds correctly. Then we've learned how to put them into a sentence, a chemical equation, and balance that equation. Then we looked at various types of reactions in the last 2 chapters we covered, 6 and 7. Now what we're going to do is take the balanced equation and learn how to do a procedure called stoichiometry. And to make a long story short, stoichiometry is a process where we follow the progress of a reaction with known amounts of reactants and predict the amount of product that would be produced. I mean, it sounds simple, but it requires some other information and techniques that I'm going to give you in just a minute. All right, these are the concepts we're going to cover, and that outline is just there for organizational purposes. We'll cover each one of these in sequence. Okay. The balanced chemical equation gives us the relative number and the ratio of moles of reactants to products. Reactants to each other, reactants to products. We can look at them in terms of molecules and atoms, but it's more useful to consider them in terms of moles of reactant, moles of compound in the balanced equation. All right, so here we have a balanced equation where, and you'll recognize this type of equation as a combustion, because one of the reactants is oxygen, which also makes it an oxidation reduction reaction. So we have this compound, and that's ethanol. the drinking kind. And then we have requires for every 1 mole of ethanol, we need 3 moles of oxygen molecules to produce 2 moles of carbon dioxide and 3 moles of water. All right, that is a balanced equation. Check it out. All right, add up the carbons, see if they are the same on both sides. Add up the hydrogens, oxygens, and you'll see that this is a balanced equation. And all it's saying is just what this is. The ratio here is established and essentially chiseled in stone. For every 1 of these, you need 3 of those, you need 2 of those, you get 2 of those, and you get 3 of those. Now you can look at it in terms of molecules, or you can look at it in terms of moles, which is much more useful. All right, here's another one. We have copper 1 sulfide, which is a solid, and we're going to react it with copper 1 oxide, which is a solid. And the product we get is copper and sulfur dioxide gas. Now, from our last, most recent study, we see that by producing a gas, we've identified a driving force for the reaction. Whenever you produce a gas, it tends to drive the reaction in that left to right direction. All right, that should be a balanced. No, it's not a balanced equation. It's not. We can see we have 4 coppers here and only 1 there. Right? So if we use our procedure for balancing the equation, we would put copper, sulfur, and oxygen. Now we have 4 coppers, excuse me. 4 copper. We have 1 sulfur and 1 oxygen. On this side, we have 1 copper. We have 1 sulfur and 2 oxygens. Right? So remember the rule, the trick. Keep those elements till last. Right? So we're not going to touch copper yet. Sulfur is already good, so we're going to go to oxygen. So how do you get 2 oxygens on this side? You need a coefficient of 2. That changes the coppers to 4, 5, 6. Okay. Now we've got oxygen balanced, sulfur balanced. We need to get copper balanced, which means we need 6 there. Okay. And that should be there. That's the balanced equation. Now that we have a balanced equation, we can do something with it. If you don't have a balanced equation, then you're not accurately describing the reaction that's taking place. How many dozen copper atoms would be produced from a dozen molecules of sulfide and 2 dozens of oxides of copper? 1 dozen of these, 2 dozens of those, makes 6 dozen copper. There we go. Or 6 moles. The ratios are fixed. 1 to 2 to 6 to 1. Now, the reason I'm emphasizing that so much is because these coefficients are eventually going to give us conversion factors. This is another way of visualizing the probably electrolysis of water. We break water apart into hydrogen and oxygen. The ratios are the same for the top and the bottom. Right? 2 moles of water yields 2 moles of hydrogen and 1 mole of oxygen gas. Or 4 moles of water will yield 4 moles of hydrogen and 2 moles of oxygen gas. The ratios are the same for both of them. 2 to 2 to 1 is the same as 4 to 4 to 2. Here's the conversion factor discussion. The mole ratio of these here will allow us to convert moles of one to moles of the other. And one rule that cannot be broken is if you have a certain number of moles of this one, let's say we have 4 moles of copper sulfide, copper 1 sulfide, 4 moles. If we want to go from here to any other place in there and find out how much of this is required, how much of this will be produced, how much of that will be produced, then we need a conversion factor. And as long as we have moles, that's the ratio, these moles ratio, then we can move from one to the other. Right? 4 moles of copper 1 sulfide. Say we want to find out how much copper it'll produce. Then we need the ratio of moles of copper 1 sulfide to moles of copper. And that ratio is 1 to 6. So we should have 24 moles of copper produced from that much reactant. Okay, here's the rule. If this is not moles, you can't move. You're stuck. Say if you have a mass, so many grams of copper 1 sulfide, you can't move because the ratios are in moles. They're not in grams. Right? So what you have to do is convert the grams to moles. That's where the molar mass comes in. Okay, so here's another possibility. Let's put this one away and look at this other equation. All right, we have sodium silicon fluoride. Sodium. Oops. Sodium. Okay, that's a solid plus, and the equation apparently is already balanced for us. And the product's going to be silicon solid and sodium fluoride solid. Okay, so they're all solids. Let's see if this is right. 2 and 4, 6 sodiums. 6 fluorides, yes. 1 silicon, yes. Okay, so we know it's balanced. Now, here's the problem. How many moles of sodium fluoride will be produced? That's where we're headed if 3.50 moles of sodium is reacted. 3.50 moles of sodium is reacted with excess. We're going to come back to this one later in the chapter, but as long as this one is excess, it never runs out. That means there's plenty, and this one will be completely consumed in the reaction. So what we have is 3.50 moles of sodium, and we want to convert that to moles of sodium fluoride. Okay, so we need a conversion factor. Moles of sodium fluoride. I'm going to leave out moles for convenience, but it's moles of sodium fluoride and then sodium on the bottom so that these will cancel. Right? And the ratio is 6 and let's see. Oh, excuse me. My mistake. 4 and 6. There we go. So we need 4 into 6 is same as 3 and 2 is 1.5. We need 1.5 times this. All right, 3.5 and then 6 times, and so I get 5.25. 5.25 moles of sodium fluoride would be expected to be produced from this reaction if we start with 3.5 moles of sodium and excess sodium silicon fluoride. All right, let's see if the okay. I misnamed the compound. This is sodium hexafluorosilicate. Here we go. That's the proper name. Okay, we're going from that compound to sodium fluoride, and we need a conversion factor. We have the balanced equation. We know what we're starting with. Right? So we need that conversion factor. And that gives us our answer. All right. Let's try another one. Propane, C3H8, right? That's the same stuff that you may be using to heat your home or run your clothes dryer, cook your food, or just barbecue outside. It's the same stuff, C3H8. And we're going to burn it. This is a combustion reaction. And it's already been balanced for us. Whenever you combust a hydrocarbon, that's what this is, carbon and hydrogen, hydrocarbon, you always get carbon dioxide and water. Well, I shouldn't say always, but under most conditions, you'll go to this. Only if you change the conditions in certain ways do you get other products. But for our purposes, carbon dioxide and water is the end result. We have 3 carbon dioxides and 4 water. All right, so we have our mole ratios of reactants and products. We want to know how many moles of carbon dioxide will be produced with excess oxygen, which makes sense because if you burn it in air, there's plenty of oxygen. You're never going to run out. And you're starting with 3.74 moles of propane. Okay? It's the same as before. The same procedure. Right? You have 3.74 moles of propane. And we want to convert 2 moles of carbon dioxide. So we need carbon dioxide on the numerator, because that's where we're headed. And we need propane in the denominator, because that's what we want to cancel. So the ratio now is 3 to 1. So we just multiply 3 times that, and we get our value. Let's see what it is. Let's see, 3 times 3 is 9, is 2, about 11 something. 11.2, I'll bet you $1. That's the answer. Okay. Right. Okay. Now, if we want to know, we know how to go from moles to moles, but we don't measure things in terms of moles. We measure in terms of mass or volume or some other easily calibrated system. So first you balance the equation. Actually, before you balance the equation, you write the compounds correctly. The compounds and the elements, as the case may be, in your reaction must be written correctly. That's why we spent so much time on nomenclature. If you're given a word problem with names of compounds only, you have to write the compound formula before you can proceed. If you can't do that, then you're stuck. Then you balance the equation after you put those compounds in the proper place, reactants and products. Balance the equation. Then if you have masses given to you for reactants or products, whatever the case may be, convert them to moles. Because remember, there's a great wall between all the reactants and on the arrow. You can't get over that wall. You can't get under that wall without moles. Then you use the balanced equation. After you've converted to moles, you use the balanced equation to set up your mole ratio conversion factor. Then once you've got the moles of the, to answer the question, then you convert back to mass. All right. So I mentioned stoichiometry at the very beginning, and this is the proper definition. Use a balanced chemical equation to determine the relative masses of reactants and products involved in a reaction. Now, this is a simplified version because you can also use stoichiometry to work with solutions. But for now, we're just going to work with masses. That's our starting point. All right. And then we're going to look at limiting reactants. That's coming. Once we become proficient at stoichiometry with masses, then we're going to limit the amount of one of the reactants. And I'll show you how to determine which one is the limiting one. Because if you don't have excess if you have two reactants and one of them is excess, then there's no problem. Right? The one that's given then is completely consumed. But if you have two reactants and they both have finite amounts, then one of them will probably run out. And that's the limiting reactant. We'll get to that eventually. So here's an example. We're going to combust chromium with oxygen. That should be yields. Right? We know this is chromium. We know that's oxygen, diatomic. What is this? Well, if oxygen is -2, and that's a -6 total, then this has to be a +6 divided into 2, which means +3. So the name of this compound is chromium 3 oxide. You ought to be practicing this. Naming compounds, practice it every chance you get. Right, now we need to balance the equation. This is easy balance because there's an element. All we need to do is say we need 2 chromium and we need 3 oxygen. Uh-oh, how do we get 3 oxygens out of a diatomic? Use our trick. Use a fraction. right? 3 halves. We'll give you 3 oxygens. Now we get rid of the fraction. Okay, this is going to be 4. This will be 3. And this will be 2. Okay, so let's clean it up. This is going to be 4. This will be 3. And that will be 2. All right. All right, we're told that oxygen is excess. All right. And we're also told that we have 15 grams of chromium. All right, that's given. All right, we balanced the equation. Well, I haven't balanced the equation yet. We're just putting our ducks in a row now. There's the balanced equation, 4, 3, and 2. All right. Now we need to convert. We need to convert this to moles. We can't move anywhere in this equation without moles. So let's do that first. 15 grams of chromium is how many moles? We need to cancel grams and leave us with moles. So whenever you see grams and moles in a quotient like that, you know it's molar mass. So what's the molar mass of chromium? Go to the periodic table. Chromium is 52.00 to 2 decimal places. Right. So 15 divided by 52 is 0.2885. I'm going to keep 4 decimal places, and even though we only have 3 over here, I'm keeping 4 here so that I can avoid rounding error. We'll bring it back down to 3 significant figures later. So this is what? This is moles of chromium. Okay. Now we need to convert moles of chromium to moles of chromium 3 oxide. And for that, we need a conversion factor. We have 4 chromiums for every 2 Cr2O3s. And so we just say that's 1/2. So we'll take a half of that value. 1442 equals. I'm going to put it down here. 0.144. Let me see if I rounded that correctly. Yeah, 1442. This is moles of chromium 3 oxide. Now we know how many moles here, but the question was how many grams. So now that we know how many moles we have, we can convert this back to grams using molar mass. So we have to calculate the molar mass of chromium 3 oxide. So we'll have 2 chromiums, which would be 52. And we have 3 oxygens, which would be 16 each. All right. And let's see, 3 plus. So I get 152.00. 152. Go. And that times 0.1442. And I get 21.9 grams of chromium 3 oxide. Okay. That is stoichiometry. Okay, this is exactly what I did. They've already rounded it off. So our answers are going to be a little bit different, probably. unless the rounding error doesn't create a problem. No, apparently it didn't. All right. That's first example of stoichiometry. You can do it all in one string, right? Just dimensional analysis takes you from one to the end. And you can do the whole calculation in one if you want. If it makes more sense to you to split it up into separate steps, that's perfectly all right. You'll end up in the same place. All right. Let's clear the board. And look at this example. Tin-2 fluoride is added to some dental products to help prevent cavities. Tin-2 fluoride is made according to the following equation. Before I show you the equation, what is tin-2 fluoride? Tin with a 2+ charge. And fluoride always has a -1 charge. So that means we need 2 of these, right? So now let's look at the equation. We take tin, metal, plus hydrofluoric acid, and that produces tin-2 fluoride, an aqueous solution, plus hydrogen gas. Okay. Now, is that balanced? Let's check. 1 tin, 2 fluorines, 2 hydrogens. It's balanced. It's already balanced for us. All right. What we want to know is how many grams of tin-2 fluoride will be produced from 55 grams of hydrogen fluoride. They should call it hydrofluoric acid because it's an aqueous solution. But we have 55 grams of that compound. And tin is excess. All right, you know where to go. This is mass you can't move. You got to convert it to moles. So we need the molar mass of HF. Right? Fluorine is 19. And hydrogen is 1.01. So that's 55 grams of HF. And we're going to convert it by canceling the grams, leaves us with moles. And the magic number is 20.01 divided into 55. And I get 2.749 moles of HF. We're going to use all of that and make this. So now we need to convert HF to tin-2 fluoride. And the magic number is 2 here and 1 there. So divide that value by 2 and we get 1.374. This is moles of tin-2 fluoride. Now we're going to convert that back to grams. Which means we need moles on the bottom to cancel, grams on the top. So what's the molar mass of tin-2 fluoride? Well, tin is 118.71. There's only one of them, but we have two fluorides. So that's going to be our molar mass. Let's see, 19. Should be able to do that in my head. And 118.71. 156.71 times 1.374, which is rounded off 215 grams of 10(2) fluoride. All right. There's a calculation in one seamless, single dimensional analyzed calculation. And there's your answer. All right. Oh, we got another one. Okay. So the last two exercises, we had an amount of reactant and we were determining how much product we would get. Okay. This one, we're going to turn the tables. We say, if we want a certain amount of product, how much reactant do you need? It sounds like it's a different problem, but it's really not. It's the same set of steps. First, you need the balanced equation, right? Phosphorus trichloride plus water yields H3PO3, right? I assume this is in aqueous solution, so that would be phosphorus acid. And then 3 hydrochloric acid. Okay, what mass of water is required to completely react with, well, actually, yeah, we're staying on the same side of the equation, to react with 20 grams of phosphorus trichloride. Okay, you can't even move from here to here without moles. So what we need is the molar mass of phosphorus trichloride. Phosphorus is 30.97 grams per mole, and then 3 chlorides. So let's find out what the molar mass of phosphorus trichloride is. That would be 137.32. So we're going to convert this many grams of phosphorus trichloride into moles of phosphorus trichloride, which is 0.1456 moles of phosphorus trichloride. Now we want to convert that into moles of water. So we need the ratio of the two. That's 1, that's 3. So 3 times that value would give us 0.4369 moles of water. Now we want to convert moles of water back to grams. The molar mass of water we've determined several times before is 18.02. Right? And that would be rounded up to 3 places, 7.87 grams of water. That's how much water is required, mass of water is required to completely react with 20 grams of phosphorus trichloride. Okay. All right. Now, we got to solve a mystery. We're not learning all this stuff just so we can pass a test or regurgitate a procedure. We're learning this stuff so we can solve problems. Here's a problem. Consider the reaction between X as an unknown element, and it's a solid, reacted with diboron trioxide, I think that's actually has a special name, diborane. And to produce this compound, plus this compound. And that's a gas. Okay. Let's see if I got that right. 6, 2, 1, and 3. Yes. Everything else looks good. All right. If 175 grams of X, okay, reacts with diboron trioxide to produce 2.43 moles of this compound. Okay. What's the identity of X? All right. First of all, what's the question? We want to know what element is X. How do you determine the element? Well, there are two ways. If you know the number of protons, right, the atomic number, it's easy, right? Every element has a unique atomic number. But I don't see any way we can get the atomic number out of this. We're not discussing protons, electrons, neutrons of any shape or form. We're talking about whole atoms, whole compounds. So the other option you have is, what's the molar mass of X? That is, for most elements in the periodic table, that is also unique. There are a couple of places where there's very close overlap between two elements and their molar masses due to experimental error, largely, and the distribution of isotopes. But for most elements, once you find the molar mass, you can identify the element. So the molar mass here would be mass per number of moles. Right? We have the mass, right? All we need is to find out how many moles is that. Okay. Our only other clue is that we have 2.43 moles of this compound. But we have the balanced equation also. So if we know the moles of this, we can convert to the moles of that. 2.43 moles of this compound can be converted to moles of that element. We just need the ratio. That's a 1. This is a 6. Right? So 6 times 2.43 will give us the moles of that element, and we can put that in our formula and determine the molar mass. Right? So 2.43 and 6 times that. That's 14.5, excuse me. Yeah, 58 moles of X. Now we can determine the molecular weight, or more properly, the molar mass. So mass is 175 grams divided by 14.58 moles. Right? 175. That's 12.0 grams per mole. So you go to the periodic table and the molar masses get bigger from left to right, top to bottom, just like the atomic numbers do. So you just follow along until you find this value. And the closest one we come to is carbon. Carbon is the element. Okay. That also tells us what this gas is. That's carbon dioxide. All right. So we solved that mystery. Now let's start to get a handle on limiting reactants. And the place we're going to go with that is called a stoichiometric mixture. If you have a mixture of reactants given to you in moles or given to you in mass or any other units, it doesn't matter. The stoichiometric mixture is a mixture of reactants in which both are completely consumed in the reaction and there's nothing left. They make products and leave no reactants behind. That's a stoichiometric mixture. Now, for as a practical matter, a stoichiometric mixture is purely theoretical. There's no way that I know of to get exactly a stoichiometric mixture. Why? Because of uncertainty. Every measurement you make has a degree of uncertainty, and you may think you have the stoichiometric amount for each one, but the uncertainty tells you that one of them is got too much and one of them's got too little. But for argument's sake, we're going to say that stoichiometric mixtures exist in the theoretical universe. That's what that statement means. Right? So a stoichiometric mixture for this reaction, the Haber process, the stoichiometric mixture would be for every 1 mole of nitrogen, you have 3 moles of hydrogen, exactly. And if the reaction on the reactants on the left of your screen are put together and they undergo a reaction, then they will produce only ammonia as product. And there will be no reactants left over. Notice that the ratio in each one of these lined areas is 3 hydrogens for every 1 nitrogen. That's a stoichiometric mixture. Okay, now to limiting reactants. Using the same example, say if we have 2 moles of nitrogen and 3 moles of hydrogen. How many moles of ammonia will that produce? Well, for every 3 moles of hydrogen, you need 1 mole of nitrogen, right? So 1 mole is required to go with 3 moles here to make how many moles? 2 moles of ammonia. And you have 1 mole of nitrogen left over. That means this one's excess, and this one is limiting. When this one runs out, the reaction stops. Now let's see what example we've got here. Okay, let's say we have, let's see. It looks like their ratio is, let's try to duplicate. Let's try to duplicate that example here and count up the number of molecules of nitrogen. 1, 2, 3, 4, 5. 5 nitrogen. And how many hydrogen? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Okay. Now what they're saying is, on the product side, you got 1, 2, 3, 4, 5, 6. You have 6 moles of product and 2 moles left over. That's your excess. So what's that saying is, if you have 9 moles of hydrogen, how many moles of nitrogen do you need? Right, so we have, the ratio here is 3 to 1. So we need 3 moles of nitrogen. That's here. We used up 3 moles of it and had 2 left over. So this is limiting. And this is excess. And the limiting reactant determines how much product can be produced. So we're limited here, so 9 moles here. If we change this conversion factor and instead put hydrogen and ammonia, we have 2 here, 3 there, and 3 into 9 is 3 times 2 is 6. Ammonia will be produced. All right. Okay. Yes, the limiting reactant is the one that runs out first. And once it does, the reaction stops. Now, as a practical matter, how do we determine which one is limiting? Because sometimes the reactants are given in mass. In fact, usually they are given in mass. So you can't tell just by looking at mass which one's limiting, because the balanced equation is written in terms of moles. So what we do is, if you have a given amount, all right, let's say you have 20 grams of hydrogen and 3 grams of nitrogen, which one is limiting? The only way to tell is to convert them into moles and then use each one to determine the theoretical amount of product that would be produced by both of them. And the one that's limiting is the one that produces the least amount of product. And we're going to do an example here. Okay. We're going to use a different balanced equation for this one. So if we have methane and water, yields hydrogen plus carbon monoxide. And that equation is balanced. A stoichiometric mixture would be, for every 1 mole of methane, 1 mole of water is required. So if you have 1 mole, you have a stoichiometric mixture in theory. Okay, what's the ratio in the picture? Well, let's see, 1, 2, 3, 4, 5. Ratio in the picture is 5 moles of methane And water is the red one, 1, 2, 3. 3 moles. Okay. Which one is limiting? Well, we can tell just by looking at this that for every 3 moles of this, you need 3 moles of that. So we've got more methane than we need. But if we were to use our other approach, we would say, how much product, let's say carbon monoxide, how much product would this one produce? 1 to 1. This would be 3 moles. This one would be 5 moles, right? Because they're 1 to 1. Well, you can tell that this one, water produces a lesser amount of carbon monoxide. That makes this one, the limiting reactant. And this one is excess. All right. Okay. As always, you write the compounds correctly from a word problem if necessary. Then you write the balanced equation. Then you convert any masses to moles so that you can move from one place to another. Then you answer the question. If the question is how many moles are produced, then you need to find out which one is the limiting reactant. Compare the amounts of product. And then take the limiting reactant and go for the answer. All right, so here we have another example. Let's take this one and work it out with a limiting reactant in mind. You react, it's given the balanced equation, so let's go ahead with that. Let's see, 3 oxygen. This is a combustion. It's also an oxidation reduction reaction. Okay. What are we given? 10 grams of aluminum. And let's see, 10 grams of oxygen. I'm going to write it down here. That's so I can do my calculations across. What mass of product will be produced given the molar mass of aluminum is 29.98 and oxygen is 32? And aluminum oxide is 101.96. Okay, so that was nice of them. They gave us the molar masses. We have to define, here's a clue. If you have a reaction like this and you're given fixed amounts of reactants, one of them is going to run out. You can make that assumption off right at the beginning. So this is a limiting reaction problem. Limiting reactant problem. Okay, let's convert this one to moles. With aluminum at 26.98. 26.98. So that's how many moles of aluminum we're starting with. That's 0.3706 moles of aluminum. Okay. How many moles of oxygen do we have? That's 32. So 10, 32 divide, this is 0.3125 moles of oxygen. Now we want to convert this. How much aluminum, excuse me, aluminum oxide will be produced from that much aluminum? How much aluminum oxide will be produced from that much oxygen? And then we compare the results. So this would be aluminum on the bottom, aluminum oxide on the top, and we have 2 here and 4 there. So that means we need a half of that. This is 0.1853. moles of aluminum oxide. And then we'll convert this one, 3 oxygens and 2 aluminums. Right? So we have let's see, 2 times. This will give us 0.2083 moles of aluminum oxide. Now we know which one's limiting. The one that produces the least amount, this one. This is the limiting reactant. This is excess. So to answer the question, what mass of product will be produced? We take this value and convert it back to mass. So we need molar mass. And it was given to us, right? 101.96 times 0.1853. 101.96 times. This is 18.9 grams of aluminum oxide. All right. So here we go with our balanced equation. Convert the masses to moles. The reactants to moles, 3706, yes. And then convert oxygen to 0.3125, yes. Then we take each one of those. We're going to do aluminum. Yeah, aluminum 1853. Yes, that's product. 2083 for oxygen. That means that aluminum is the limiting reactant. Then we go with the amount of the limiting reactant and convert it to mass of product. All right, this just emphasizes the point that you cannot work from mass to find the limiting reactant. There's no way, it just doesn't happen. Because the reaction is in terms of numbers of atoms and numbers of molecules. All right. So the point of this slide is to hammer home the value of knowing the limiting reactant. If for this reaction, if we start off with 2 moles of hydrogen and 2 moles of oxygen, how much product will we produce? Well, you need a ratio of 1 to 2, right? So you need 2 of these, but you got 2 of those. You only need 1 of them. So this 2 is going to be 2 to 2. This is going to give us the same amount of water. That's A. If you have 2 moles of hydrogen and 3 moles of oxygen, still, you got excess oxygen. You only need 1 mole here to match that 2. So we're producing 2 moles of water out of that mixture. How about this one? If you have 2 and 1. 1 to 2, 1 to 2 makes 2. This is your stoichiometric mixture. And D, how about D? 3 moles of hydrogen and 1 mole of oxygen. 1 mole of oxygen. In this case, oxygen is limiting. And we have excess hydrogen. So 1 mole of oxygen is going to make 2 moles of water. And each produces the same amount of product. That's the answer. There you go. All right. We're back to the Haber process. How many grams of ammonia can be produced from a mixture of 3 grams each of nitrogen and hydrogen? All right. So we have N2, 3 H2 yields 2 ammonia. And we're starting off with 3 grams each. Okay. So we have to find out which one is limiting before we can tell how much of this one are produced. And so what we need here is a conversion factor to make moles. 1 nitrogen is 14.01 grams. 2 nitrogens in this molecule would be 28.02. So 3 divided by 28.02 is 0.1071 moles of nitrogen. How about hydrogen? 1 atom of hydrogen, or 1 mole of hydrogen atoms, would be 1.01 grams. Since it's diatomic, that would be 2.02. So now we need 3 divided by 2.02, which is 1.485 moles of hydrogen. Now we want to convert each one of these to ammonia. Okay, so we need our conversion factor for each one. Hydrogen on the bottom here, nitrogen on the bottom here, and ammonia on top for both of them. What's the ratio? Well, 2 for the ammonias, 3 for the hydrogen, and 1 for the nitrogen. Right. So this one's going to be 2 times this value would be 0.2141 moles of ammonia. And then 2/3 of that value would be 0.9901 moles. So we know which one is limiting. The nitrogen. Nitrogen is limiting. Right? That means that 0.2141 moles of ammonia are produced. And was it asked for grams? How many grams? Yes. So the question is grams. So we need to convert this one back to mass. Okay. We need molar mass for ammonia, 14.01 for that one, 3.03 for the hydrogens, because it's 3 times 1.01. So that's 1704 times 0.2141, which is 3.65 grams of ammonia. Okay. There's our conversion of nitrogen to moles of nitrogen, hydrogen to moles of hydrogen. And then, all right, what they're doing is saying the ratio here is 1 to 3. This is another way to do it. If this is 1 to 3, then you need 3 moles of hydrogen for every 1 mole of nitrogen. So if we have this many moles of nitrogen, you need 0.3, approximately 0.3 moles of hydrogen. How much do you have? You have 1.4. You have plenty of hydrogen. This is the excess. Right? That's another way to do it. I like to do it this way because it's foolproof. Plus, it already gives you the moles of product that you're after. Then you just take the one that's limiting and convert. There we go. And yeah, 3.65 grams. All right, I think this is the last, yes, this is the last concept we're going to introduce in this chapter. And it's called percent yield. Percent yield speaks to the problem of efficiency especially for chemical engineers. Those who are charged by a company with producing the maximum amount of product from any given reaction. Some reactions are difficult to produce large amounts. They may be maybe 10% of the expected amount. So it's for chemical engineers, this is a life or death situation, unemployed versus employed situation. What you need to know first is the theoretical yield, and we've already determined that. What's the theoretical yield for this reaction? Right? Even with limiting reactants, we can produce a theoretical yield. That's what we've been doing so far. What's the maximum amount that we should expect from the reaction? And then the actual yield is what is measured. So you have to be given that value. What is the measured amount that's recovered from this reaction? Various problems can limit the amount of actual yield. Right? You could have, in the reaction itself, you could have what we call side reactions. Those reactions that go direction we don't want. Right? That can happen and produce less of the product that we want. Or your problems could be in recovery, right? Because you've still got this mixture, unless one of the products that you want is a gas, and it can be, and it's the only gas that is evolved from the reaction, then you can recover that gas with good efficiency. But still, you might lose some in the process. Any type of cleanup operation is not 100% efficient. So you get the value, the actual yield, from a measurement. And then all you do is ratio the two. Actual yield divided by theoretical yield times 100 is the percent yield. Now very often these values come in the form of mass, right? Mass of actual yield divided by mass of theoretical yield times 100. But it could also come in terms of moles, in which case you might get a different value. Because when you measure grams, let's see. No, moles should give you the same value, a percent yield. If you have actual divided by theoretical times 100, and you have mass, right? Mass divided by mass times 100, right? What if you have moles instead? If you convert grams to moles, right? And that gives you moles per mole times 100. These two numbers are exactly the same, right? Because it's relative to a particular product. So this value is going to be the same as that one. Cancels, cancels. It gives you the same value. So if your yield is in grams, you can ratio the actual to the theoretical, or if it's in moles, you can ratio the actual to the theoretical, and you get the exact same percent yield value. All right. So let's try an example. In this case, we have this equation. 2 sulfurs plus 3 oxygen yields 2 sulfur trioxide. And we're given 1.50 grams of sulfur trioxide is produced from 1 gram of oxygen. So actual equals 1.50 grams from 1 gram of oxygen. And I assume we have excess sulfur. Yes, excess sulfur. So what's the percent yield? Well, if this is actual, we have to calculate the theoretical. What's the theoretical yield? So if 1 gram of oxygen is going to be converted to sulfur trioxide, we need moles first. That's 32 grams of oxygen per mole. So 1 divided by 32 is, let's see, 3.125 times 10 to the minus 2 moles of oxygen. Then we want to convert to moles of sulfur trioxide, which would put oxygen on the bottom, sulfur trioxide on the top. And we have 2 here and 3 there. So 2/3 of that value would be 2.083 times 10 to the minus 2 moles of sulfur trioxide. Now we have an option here. I've already said that the ratio of grams to grams is the same as the ratio of moles to moles. So we can either convert this one to moles and ratio of 2, or we can convert this one to grams and ratio the grams. We'll do that one first, or only. We're still going to have to find out what's the molar mass of sulfur trioxide. So sulfur is 32.07, and then 3 oxygens. Right? So that's 48 for the oxygens and 32.07 plus is 80.07. So this is moles on the bottom, grams on the top, 80.07. And that's, let's see, times. This is 1.67 grams theoretical. SO3. Now we can do percent yield. Right? 1.50 divided by 1.67 times 100. Which is 89.9%. Rounding error, 89.8%. So we converted. We actually found out what the theoretical yield was in mass, and then ratioed the two. Okay? But you can do it in moles also. Works both ways. All right, one last problem. And this one takes some thinking. A lot more thinking that we've done so far. If we have P4 and 6, let's see, fluorine, yes, yields 4 phosphorus trifluoride gas. What mass of P4 is needed to produce 85 grams of PF3? And this is actual. That's the amount we want to recover if the reaction has a 64.9% yield. 64.9% yield. Okay. So we could convert this to moles and work back to here and convert that to grams after we find out the moles. But that would only be the amount that would produce this if it were 100%. What we need to find out is what the actual amount is. The theoretical amount. Find out the theoretical amount. Go back to the formula. Percent yield equals 64.9%. Okay? So if we want to find out, and that's equal to the actual divided by the theoretical times 100. Okay, so we got this number. We've got the actual 85.0 grams. And this is our unknown. Right? So solve for the unknown. Bring the theoretical over here. And then you got 85 over here divided by 64.9 times 100. Okay. So let's calculate the theoretical. 85, enter, and 64.9 divide times 100. And that's 130.97 grams. That's the theoretical amount of PF3. That's the one you want to convert to moles to go back to here, because then that will give you this amount that will theoretically produce this amount, but with this efficiency only produces that amount. Okay, so we need to convert this one grams per mole. We need to find out the molar mass of PF3. Right? I think we've done this before. 30.97 and then 3 times 19. Yeah, 87.97 grams per mole. Okay, so we're going to divide that into 130.97, and I get 1.4889. No, 888. Let's round it to 9. Moles of PF3. So now we can convert that number of moles into moles of PF4. Okay, so we need to cancel this one and leave us with this one. And the ratio is 4 here and 1 there. So we divide that by 4. And that gives us 0.3722 moles of P4, which we need to convert to grams. So what's the molar mass of P4? Well, this is 1P, 30.97 times 4. Which is 123.88 grams per mole. 123.88 grams per mole times 0.372 is 46.1 grams of P4. All right. All right. So this is the step where we find out what's the theoretical amount of PF3. And this is a single step calculation that gives us that gives us the actual amount of P4 required. All right. I think that was the last slide for today. Let's see. Yes, that's the last slide. And okay, so we've covered chapter 9 lecture. Next thing we have to do is a review using the review document. Only in my in the syllabus, the schedule gives us next Tuesday as a buffer day. So I think what I'm going to do is go ahead on that buffer day and start the review. And if I can finish the review on that day, then the following day, I'll just following Thursday, this is Thursday, next Tuesday, we'll do a review. If I can finish it then, fine. If I can't, I'll go to the Thursday and finish it then. Or if I have finished the review on next Tuesday, I'll go to Thursday and just show up here in class and Zoom so that I'll be available for questions from the class, anybody that wants to Zoom in. And then the exam for this chapter would be on the following Tuesday, 2 weeks from today. No, actually the exam is on the 19th of March, because right after we do the review is spring break. So you got spring break, and then that following Tuesday after spring break, we have the exam on this chapter is due. Okay, that's it for today.